Swayam Prabha. Digital India. Educated India.
Okay, now we are still stuck in our problem one, but it turns out that we can go deep, and then we can. We are now discussing a little bit advanced quantities like correlation coefficient. So the coefficient of determination, for some reason, statistically, from the science of statistics, somebody called it R squared. I don't know why. So it has stuck that name. So coefficient of determination is R squared. The root of R squared is the correlation coefficient or coefficient of correlation. Sometimes it is expressed as 0.7, 0.8, 0.9. I would like to call it as 90%, 95%. Both are one and the same. So this basically, so you please remember the height of students in a class versus the age. The original variability in the data minus the variability in the data after you fit the correlation divided by ST. So if SR tends to 0, R square will tend to 1. So this is an ideal case, but it should not be so close to 1 that somebody suspects, because whatever you do in your experiment, whatever be the accuracy, there will be natural variability, there will be natural error. So in an experimental correlation, if you get R equal to 0.9596, it is very good. If it is Sir, make a note on what are you saying, Rajesh? All right. So we want a R square which has to be as high as possible. Okay. So after that, what you can do is so this is as usual, it is not coming properly. So this can be, so this is basically data. Okay. Okay. After you finish the correlation, let's say, so this is 25, 20, 15, 10, I don't know, some example. Degree centigrade, this is degree centigrade. So 10, 15, 20, 25, 30. Let's say somewhere instead of 25, for 25 you're getting something like this. For 20 you're getting like this. So you're expected to get a scatter like this. So this is called a parity plot. So after you develop a correlation, it is a good healthy practice to draw a parity plot. This will give you a visual idea. So this will give you a number. This will give you a visual estimate. This will give you a visual idea of how the data are spread about how good the correlation is. I'll discuss more fundas about this. But first before I forget, I will write the other names for this. Parity plot, scatter plot. It's also called a scatterogram. So now, okay, so this is the name for this. So it's a good idea whenever you're doing a correlation, whether based on neural network, this thing, regression, multiple linear regression, non-linear regression, whatever. Finally, there is a fit. There is a data. Compare the data with the fit. Okay. Rajesh. So this 45-degree line is called a parity line. The parity plot clearly tells you if the points are equally spread or the points are uniformly spread above the parity line, about the parity line. So since it is a best fit line, approximately half the number of points will be above the parity line, half the number of points will be below the parity line. But just don't keep checking this and all that. Generally, it will be true. And also, the spread will be more uniform like this. If I have a parity plot like this, so So it is like this, and suddenly here it is like this. That means whenever this is y data, y fit. Whenever the y data or y fit is very high, there is too much scatter. That means suppose you have fit a linear, you did a linear fit to this. So t equal to a dt is not an adequate fit for this. So it just tells you that there is some higher order effect. Could be a variable thermal conductivity, variable properties, or there is some other physics going on. So the correlation coefficient or the fit can be only as good as the data or as good as the physics. You may be a stud in data science. It's not going to solve the problem. If your original forward model, if your physics is not right, whatever data you use, you will not get the result because there is some hidden physics which is missing. So the idea in data science is just to find out if the data can solve all your problems. Okay, but that all sorts of problems cannot be solved. Okay, with just pure just brute force data. Okay, if it is like this, then you have to revisit your data and then figure out additional effects. Now, another case could be there is one fellow like this. So he is called an outlier. So it stands to reason that this outlier, there is some gutbud with that point. Either there was a voltage fluctuation, or you just dozed off, you took the wrong reading, you went for chai and somebody disturbed it. You have to do the experiment under controlled conditions with no wind. There is a fan in the room and you tried your level best, so nobody switches on the fan. Some mechanic came and switched on the fan for 5 minutes, it disturbed. So some gutbud took place. Therefore, this point has to be removed. So that is not cheating. Okay, it is a bad point, you can remove. So if you have 100 points, you can cite CIT the reason of poor data quality, and you can remove up to 5% of the points. Either remove it directly or remove it and replace it by another point. Okay. So this outlier clearly says that there is some problem with that point. Okay. So this is as far as correlation coefficient and other things are concerned. So you can draw a parity plot, you can do a correlation coefficient. You can also get the standard error of the estimate, correct?
Sir,
yeah.
How do we find T fit in terms of T data? Like,
what is that?
How do we find T fit as a function of T data? Like,
T fit as a function of data. T fit equal to a plus bxi. Substitute the value of x. Anyway, you are getting a and b from the equation. Get T fit of I. What is the problem?
So the plot is against like T data and T fit, right? The T
Correct.
data is on the x-axis, so the
Correct.
plot should be with respect. Like, how do we make the plot then? Like, so along the x-axis we have the T data, and along the y-axis we have the T fit. So,
what is the problem? What is bothering you?
The plot is between these two functions, right?
Because you've never been taught like this from high school onward. You thought that plot should also be x and t, y and t. I'm saying there is a particular value of x. For that particular value of x, there is a temperature data. There can also be a fit data, correct? Based on a plus bx. Use only these two values. Forget about your x. You understand?
Yes, sir.
That is the way, because so much you studied so much in life based on some particular concept. The scatter plot, many people first time when you encounter scatter plot, you don't know what it means, because throughout your teachers told you dependent variable, independent variable, two dependent variables worked out by two different means can also be plotted. That is the parity plot. Don't ask for the x in the problem or time t in the problem. It is the x or the t is the same for both the quantities. We are comparing two quantities which have been obtained by two different methods, one by measurement, one by fit. They are, each of these points has a particular x which is hidden, which is not of primary interest now for understanding the nature of the correlation coefficient. Is that clear?
Yes, sir.
Okay. So good question, because because this is the first time you are learning this, so you'll have that doubt. Okay. Any other question? Shall we proceed? Okay.
Sir?
Sir?
Sir,
Yes.
then basically we'll be saying that on the parity plot, each point is specific for a predefined x.
Let it be specified, but that parity plot gives the complete story. It gives the complete story of the temperatures in the problem.
So
I don't worry about x now. I'm just saying that for each predicted value of x, how close is it to the true value?
yes, sir.
See, basically, plot is only to help. We should not become a slave of maths. What I want, what is the goal? I want to compare between this. I want to compare data and measurement. I can use whatever tools I want. The other way of doing it would be just plot two lines. Okay, take x-axis. In the x-axis you put x, y-axis you put t, and then draw the 2 points and draw the 2 lines. That is dumb. That is what is done in high school. Now we do a little better. Okay, we just plot the 2 quantities directly. It will be very revealing. Okay, we can also do what you have done. So in fact, we go even further. When you do research, we will take rainfall predicted and rainfall observed, and we will give a third plot which is called the anomaly plot, which will give you the difference. So which will give you the difference between a predicted quantity and observed quantity as a color contour. Here we will show the regions where there is a maximum error in rainfall, wind speed, cyclonic circulation, whatever. This is in atmospheric science. In other places, the anomaly in temperature contours, where the error is more in the prediction and so on. So creative plotting is an art you have to learn, which is not taught, which cannot be. So you have to figure out creative plotting. If you are to be a serious researcher, even if you have to be a manager, if you want to impress your funding agencies, even if you have a startup, you want to venture capitalist, angel investor, you want to find. So you should develop and you should understand. You should come out with stud ways of plotting. Okay. Okay. Creative plotting is important in research. Okay. All right. Let's get back to that problem. I have what is that? PPT. Okay. I created a folder now. Wait. Okay. Now what I should do is I have to share the screen. Correct? Where is this? Okay. Now you have to tell me whether you're able to see the screen or not.
Yes, sir.
Okay. So I have to do some more things like slideshow from beginning. Okay. Is this okay? Now, since right side I'm seeing Rajesh Akula, Suraj Kumar, Varshini, those people who spoke, I have to minimize so that I figured out. Okay, so this is our problem which we have been stuck for the last 1 week. There are 6 temperatures and you want to get the heat transfer rate, heat flux. Okay, now all of you just please evaluate, just check what Suraj has done. Okay, this is Suraj's work. Get the correlation coefficient. Just spent already, it is an online class. Already it is not as good as a real class. If you just copy it from the board, it doesn't make. Hey, are you able to see me?
Yes, sir.
Very good. So just to take that first column is serial number, second column is X, third column is data, T data, fourth column is X, Y, X, all that you have done. Now, last 3 columns, you work out now. Okay. So please go to the bottom of the table using least square, A equal to 83.8, B equal to 15.97. Is something close to what we, or use the actual values which we figured out in the last class. Based on this, again revisit the table and go to 1, 2, 3, 4, 5, 6, column number 7. Okay. Column number, go to this column number 7. Okay. Sorry. Go to this column number 7 and calculate the y fit. Then calculate the y minus y bar square, y minus y fit square. Then you will be able to get the ST minus SR divided by ST. Okay, then you will be able to get it. Please work out the correlation coefficient. I'm going to wait for 5 to 7 minutes. If somebody doesn't want to work, you want to take a water break, it's okay, but it's up to you. Okay. At least next 5 minutes, I'm not going to speak. I'll just stand here. If there's any doubt, you can ask me. Just work out the last 3 columns, please. Otherwise, you'll be stumped by this in quiz 1, quiz 2, and all that. Okay. And then just check whether the values which we are getting is correct. A and B values, we already got it. Anyway, the formula is there. Now, this PPT anyway is available in the form of a lecture. We'll also try to make it into PDF and give it to you. Okay. Don't copy from PPT. Huh? If somebody has finished, you can let me know. I'm sure you're going to get values slightly different. Whatever values you're getting, we'll write it on the board. But for starters, please let me know what we got A and B the last class. A equal to?
So A is minus 83.914.
Okay. B?
15.97.
Okay. Oh, now? Yes. In simple English, I want the 4 boxes to be filled. I want the 4 boxes to be filled. So please note that Varshini told that it is 83.9. So what I put on the PPT is 83.8. So some slightly different values you will get. So there's no point in directly copying from the PPT. Huh? No, wait. Somebody is coming on chat. How do I see that? Huh? Hey, can I not stop sharing screen and still look at the chat? How do you do that?
Sir, minimize the presentation.
Minimize the presentation. Wait.
When you share the screen.
Oh, when I minimize the presentation, it goes somewhere. No. That is causing me anxiety now. Huh? I will. The screen sharing is paused. Something happened.
Yes, sir. Now
Change
we won't see.
I will. Now can you see? Can you see or no?
Yes, sir. We can.
Okay. So I think somebody came. I don't know how to do that. Let's not. I don't want suddenly it says you ended the meeting for all. Huh? Yeah, please tell me what is STSR, and then we'll be done with this. So one, anybody? Huh? Varshini, did you finish?
Sir, not yet.
Okay.
Sir, SR is 1.106.
Sir, ST is 13.4284.
Very good. Okay. Now, already it is very clear. Okay, that is Subhash, right?
Yes, sir.
Very good. Thank you. So you see the funda. When you just use the mean, the variability of the data was 13.43. That means you are just saying that the temperature in the slab is something like that. That is the average. So that is the best you could do if you didn't know heat transfer. If you only a data science person, that means you know only statistics. You will say that the temperature is some average temperature plus or minus 3 sigma if it is Gaussian. I will tell you what Gaussian is a little later on. Already you know that. So that is the best you could do. Compared to that, now I put a fit. Therefore, out of this 13.43, 12.3 are already explained. Only 1.106 is still remaining. What is remaining? 1.106 is the remaining variability in the data. That's because of an imperfect fit, or there are some errors in the measurement and so on. Now, obviously, the R square is going to be terrific because R square is basically 12 by it is very high, no? It is 12.3 by 13.4. How much is this?
0.9176.
R square 96, 95. How much is it? I'm just doing bindas. What is the one? What is the value?
0.958.
96. Okay. So 96% is not, you're not badly off. Okay. Fine. So all of you, I think, so all of you should try to complete this, and you should get the R squared and the R and take the problem to its logical conclusion. Okay. Now this is basically, this is like what you guys wanted. Okay. Temperature in degrees centigrade versus X. So you can just put it on Excel. Excel will give it in no time. But the problem if it's multiple variables and if it is non-linear, if the form is not linear, okay, if the form is not linear, you can't use simply Excel and solve this problem. You cannot trivialize the problem like this. Okay. And also the most important thing, I'll talk about this a little more when we go to statistics. Correlation. So I will stop the presentation. Okay. Correlation is different from causality. Okay. They are two different things. You can have a high correlation, but it need not be this need not be the cause. Yes. Let's say last 20 years, you just see the last 30 years, the number of rainy days. Number of rainy days in India, for example. Rainy days defined by India Meteorological Department as average rainfall more than 5 millimeters, something. Average number of rainy days. Okay. Okay. This is one. Then take some other quantity. I don't know what quantity is good to compare. Average alcohol consumption in the country or something. Then if you plot X versus Y, suppose you get a correlation and then say that whenever it was raining, people started drinking. This is a hypothesis, but we don't know whether it is true or not. Okay. So a high correlation can be quite different. 1 + 80 is problem. Okay. high correlation need not imply causality. So sometimes you get so enamored with or enamored by, or you get so impressed with data science. With data, you can do anything. Garbage in, garbage out. I mean, if you don't know the physics, data will keep coming out. Every time somebody uses a smartphone, smartwatch, data will come out. How to make sense of the data, right? And particularly when you're doing a scientific problem, you have to, whether there is a causation. Causation can be obtained only from empirical evidence or from your knowledge of theory and so on. So blind statistics cannot take you very far. However, if there's too much data, it's good to know the method so that there's a scientific way of handling it and all that. So data science, use data science with caution. Okay. So that caution is very, very important. Now, we have to get back some descriptive stuff. Okay. So we'll just take a quick breezy overview of statistics. Okay. Now, before that, there's something which I wanted to tell you, but last 6-7 classes have passed by, and then I don't want to write on the board and spend more time. Just take down these key points. Applications of inverse heat transfer. Okay, I should have said it in the first class itself. Now it is the 7th class or the 7th lecture, but it's good to state it now. So you have an idea what an inverse heat transfer is all about, and I talked about data, causality, correlation coefficient, data science, physics, a forward model, inverse model. So you've got a good idea now. So you already have a good idea of what inverse is all about. Applications of inverse in heat transfer. First, estimation of thermophysical properties of materials. Somebody is persisting. Sorry, hey Siddharth. So applications of inverse heat transfer are estimation of thermophysical properties of materials, thermal conductivity, emissivity, specificity, diffusivity, and so on. Estimation of boundary heat flux in forced convection. We saw the boundary heat flux now in conduction. That's what we did, Q. You can also have estimation of boundary heat flux in forced convection. You know that will be a lot more difficult. Estimation of spatially varying heat transfer. This is a nightmare. This is Suraj's PhD. Suppose the heat transfer coefficient is a function of x and y or x, y, z. It's a very tough problem to solve, tough inverse problem to solve. Estimation of contact conductance. Oh, this is a sore thumb. Okay, I make a sandwich. Okay, it is lunchtime, so you may conjure up visions of a sandwich with green chutney and all. This is sandwich in thermal engineering. Okay, so this is one material A. So this is one material B. So this is one material C. So this is called sandwich construction. Sandwich construction. Okay. Sandwich of various materials. I'm putting a sandwich construction. Why am I using sandwich construction? Because I have many things. One could be an insulator, one could be a light material. There are so many. This thing. One could be steel, one could be aluminium, one could be copper, one could be asbestos, one could be rock wool, mineral wool, whatever. Wood, this thing, whatever. Plywood. There's some apply. I have many applications. It could be a wall, it could be an auditorium. Okay, it could be a computer center. It could be just partitions in in a IT company office, whatever. So I am using what is called a sandwich construction. Now, sometimes in a sandwich construction, I want to join this A and B. I will use there will be some imperfect contact here. Whatever, I may use some brazing, okay, welding, then I may use some riveting, so on and so forth. I may use some other, but what will happen is, so there will be an imperfect thermal contact. Suppose this is part of a space vehicle, okay? It's part of a satellite, which has got a big 800 crore payload. There's a 800 crore payload in your GSLV, and it is blasting off 36,000 kilometers. It is putting it in a geostationary orbit. And then you figure out that the heat transfer professor or the heat transfer scientist in the group, the heat transfer group, forgot the contact conductance. So they are asking that sensor that something has to be measured and something is malfunctioning. Then you'll have to figure out, then the problem could be you did not estimate. What is it you did not estimate? So simple heat transfer, no? If the heat transfer group is doing the calculation, they will say that this is all 3 resistances in series. Okay. KA, KB, KC, LA, LB, LC, then you will do all that, right? So you know how to do it. So you will do all this, right? What will you do? You will do this. So this is T1, T2, T3, T4. These are the interfacial temperatures, T2 and T3. So this is resistance A, resistance B, resistance C. So you learn from the best heat transfer books. You also learned online lectures from MIT, IIT, this thing, IIT Bombay, IIT Madras, Kanpur, Kharagpur, whatever. Okay, and you estimated. But you didn't know when two things are joined, there is a strange animal called contact conductance. This contact conductance is between second and third. Let's say there is one more conductance called R contact, which you forgot. So this will make your solution go for a 6. If it is serious, everything will change. Everything will change. Therefore, this has to be treated as an inverse problem. What you do is you make this sandwich construction in the lab, and if it is a high vacuum environment like outer space, make a vacuum chamber, put liquid nitrogen, liquid oxygen, circulate it, blah 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 blah, and all that, and then ask a PhD student. There'll be a prof who will take a project with a prof like me. There'll be a PhD student like Suraj. They will do the experiments in 2-3 years. We will tell you. And sir, why inverse problem, sir? I'm a super stud in heat transfer. I will directly get the contact conductance. Oh, how will you directly get the contact conductance? Please note that the contact conductance will be a function of what these two materials are, the surface roughness, how much pressure you are applying, what is the joining technique. So it is very customized. So only crying child will get milk. Everything is not available on Google. So if you have got a 800 crore payload and the heat transfer is critical, you better do the work. There is no shortcut. You'll have to do the work. It will take 6 months, 1 year, 2 years, do the experiment, do the inverse, do the sensitivity analysis, find out the standard deviation, all that, and fix it. Okay, you'll have to do that. Okay, it's well worth it. Okay. Now, estimation of bulk radiation properties. Okay, so for electronics is generating heat in a satellite. So I want to cool it. So I will look at the direction in which the satellite is not facing the sun. So the outer space can be considered to be a very cold surroundings at 3 Kelvin. Okay, if it is not facing the sun, then no, forget about cosmological radiation, cosmic radiation, all that is small quantity. Okay, now your device is at 250, 300 Kelvin, outside is 3 Kelvin. So epsilon sigma T to the power of 4 minus 3 to the power of 4 is terrific. But the critical quantity there is epsilon. Emissivity. Who will tell you that emissivity? It is not available in textbook. It is not, the knowledge is not available in textbook or research paper. Knowledge is not available with a professor also. Knowledge has to be obtained only you do it. You have to do the experiment. Theoretically, it cannot be found. Everything cannot be found theoretically. You have to again put a vacuum chamber, test it, this thing. Because it is going to be on your critical mission inside 3D, inside 3E, whatever. Or you want a renaissance, what is that? It's not renaissance, what is it called? Reconnaissance aircraft, reconnaissance this thing, satellite, spy satellite, whatever do you have this thing. So you have to figure out what is the emissivity of the paint you want. Then there are some bulk radiation properties with which your CT scan. From CT scan, you're predicting a cancer. So that's it. So you have to know it basically depends on the absorptivity of the tissue. So you'll have to characterize it, tissue absorptivity. So in all these applications, the inverse is a very important thing. Okay. So you must understand the principles of statistics. You must understand the principles of measurement. You must understand the physics, the forward model. You must understand data science. You must understand regression. You must understand neural network, everything. And you should finally, uncertainty quantification. You should be able to tell clearly what is the error associated with this estimate. Okay. Then you are a complete scientist. Okay. Now let's go to the next subchapter, statistical description of errors. We actually used it in our correlation to T equal to A plus BX. Okay. Now we have to statistically describe the errors. How do you describe the error? How will you describe? Okay, we'll say no in high school and school you would say describe in 100 words, describe in 200 words. Now our description is all mathematical or statistical. How do you statistically describe errors? Now, what is the motivation for studying statistical description of errors? The first bullet, Accuracy of inverse solution is a strong function. The English problem is there. The screen sharing is sharp. So accuracy of the inverse solution is a strong function. Okay, please fill up all that. Indefinite article, definite article. Accuracy of the inverse solution is a strong function of the errors involved in the measurement. So the funda there is the measurements are to be statistically described. First and foremost, errors are additive. Okay, that means a measured equal to actual plus the error. Sir, it is so obvious. No, don't think everything is so obvious. So if it is additive, I mean it can also be subtractive. That means error can be negative. But the error is not multiplicative or divisive. Are you getting the point? Measured error is not some alpha times of actual error. That means there is a problem with the proportionality. We can deal with it. There is something wrong with the measurement, the scale. So the measurement error is additive. First point. And the errors have a zero mean. If you add all the errors, if it is an unbiased instrument, it has a mean of 0. That means sometimes it is plus 0.4 degrees, sometimes it is minus 0.5 degrees, sometimes it's plus 0.6 degrees, sometimes it's just plus 0.1, minus 0.2. Sigma over a large number of readings will result in a zero mean. That is why we say the mean or the expectation. The expectation is defined by capital E. Capital E of epsilon I equal to 0. The errors have a constant variance. So the variance is independent of the measurement. Please note that when I formulated, the variance can also be a function of the measurement. That won't be a simple least squares. It will be what is called the weighted least squares, WLSR, weighted least square residual method, which we will discuss a little later. It's a little bit advanced. After some time, we'll discuss it. I will solve one problem with that also. The errors associated with different measurements are uncorrelated. Please note that this is a very, very important point. The covariance of epsilon 1, epsilon 2, epsilon blah, blah, blah is equal to 0. Okay. While this mathematics may be scary to some people, what I'm saying is there should be no way by which you can get the error in the fourth thermocouple if you know the error in the first thermocouple. That is what I'm meaning by saying that they are correlated. If they are correlated, you will anyway use your fundas and say that so with one error, I will find out all the errors. Then this game of statistics will come to a close. The game has to be played because the errors are random. So there's a random, that is why it's a random variable. It's random. So you cannot use any stat quantities. It's like, so the random number is, what is a random number? A number which comes later in the sequence cannot be put as a function of the previous number. That is a random sequence. Like that, it's an uncorrelated error. The fifth thermocouple will behave according to its dharma. But we will know that the average, the variance will be like this. It will be Gaussian plus or minus 3 sigma. But exactly whether it is 0.1 or 0.2, it won't know. It will behave according to its own. The measurement errors follow a Gaussian distribution. Okay. So this Gaussian distribution is one of the stud things. Is one of the most stud things. Okay, or normal. Okay, it is a normal distribution. Okay, so f of epsilon I it follows this. Okay. So that root of sigma square can be taken out. I've written it as sigma is outside the root. That's also okay. Minus epsilon I square by divided by 2 sigma square. So this when you plot, it becomes like this. Then the integral is actually the probability that we will see a little later. So Gauss, amazing person, right? Amazing. He's called the prince of maths. Okay. So I will stop the note now on Gauss. So his school teacher, the school teacher said 1, 2, 3, 4, 5, blah, 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 up to 100. What is the sum of these numbers? Okay. This sum of these numbers up to 1 to 100 without. So Gauss immediately gave the answer. Okay. How do you do that? Huh? You figured out that each of these is 101 into 50. Huh? So this, I believe he did it as a school kid. Huh? So Gauss is a great Guruji. Okay, he's called the Prince of Mathematics. Okay, so his contribution is just mind blowing. Okay, so I'll stop on that note. We'll have more to discuss. Any questions so far?
Sir,
Is
one point is like errors have constant variance. Can you just elaborate on that, sir? Like in the PPT, one point was mentioned that errors have constant variance. How can we correlate? Means how can we interpret it? Like different errors
No,
can have different variances, right?
no individual errors, but in this analysis, the first level analysis will be same. After that, I will not have that. I will not have that restriction. Is it okay?
Okay, sir.
For simple least square, it is. I will also say that prior knowledge is not available. All that is for simple least square. Then slowly this is for elementary. Once we go deep, all this can be, what you say is correct. Sigma 1 can be different from sigma 2. Only if you know, then how will you know the sigma 1, sigma 2, another story. So it's better to take one sigma square, which is some average and this thing and proceed. So it can be different. All the theory is okay, but you are an experimentalist, you are in the field, you want to know, means it's better to have an average sigma or something like that. In principle, it can be different. Is that okay, Anand?